Right now, in the daytime sky, the sun looks utterly dependable, a small, steady, golden disk you could block with your thumb held at arm's length. It has looked that way for the whole of human history, and for billions of years before anyone existed to look up. But the sun is not fixed. It is a furnace slowly consuming its own fuel, and every furnace, however patient, eventually runs low. This is the story of what happens next. How a calm, middle-aged star becomes something closer to a monster, swelling until it swallows the world nearest it, then the next world after that, and very likely ours as well. How it sheds itself into space in a slow-motion catastrophe with no explosion at all, and what is finally left behind, a small, hot, dim ember, quietly cooling for far longer than the universe has yet existed. From Earth, the sun looks like the most reliable object in the sky. A small golden disk about half a degree wide, small enough to block out entirely with a thumb held at arm's length. It rises, it sets, it warms the day, and it has done exactly that for the entire span of human memory. But the sun a person sees today is not a fixed thing. It is a star roughly halfway through the one stable, productive phase of its life, a phase astronomers call the main sequence, and it has already been burning through that phase for about 4.6 billion years. At the sun's core, temperatures reach about 15 million degrees Celsius, and pressures reach hundreds of billions of times what a human feels standing on Earth's surface. Under those conditions, hydrogen nuclei are forced together tightly enough to fuse into helium, a process that releases an enormous amount of energy as light and heat. This is nuclear fusion, not the ordinary chemical burning of a candle or a campfire. There is no flame and no oxygen involved. The sun is not on fire in any everyday sense. It shines because atomic nuclei are being fused together at its core, and the leftover energy has to go somewhere, and that somewhere is outward, as sunlight. This fusion creates an outward pressure, a kind of internal push, that exactly balances the inward pull of the sun's own gravity. Gravity is always trying to crush the sun down into a smaller, denser ball. Fusion pressure is always pushing back outward, trying to puff it up. For most of a star's life, these two forces settle into a stalemate, and the star holds a stable size for an extraordinarily long time. This balance is the reason the sun looks the same today as it did to someone standing on Earth 100,000 years ago, and it is the reason the sun's calm, steady light can be trusted to warm a planet for billions of years at a stretch. But it is a stalemate, not a permanent peace, and the terms of that stalemate are set by a resource that is finite, the hydrogen fuel sitting in the sun's core. The sun does not fuse hydrogen from its entire body, only from a dense central region, the core, which holds only a fraction of the sun's total mass. Everything outside the core, the vast majority of the sun's bulk, is just along for the ride, too cool and too low in pressure to fuse anything. To grasp the scale involved, it helps to shrink things down. If the sun were shrunk to the size of a beach ball, roughly 60 centimeters across, Earth would be a grain of sand orbiting about 6 meters away, and the fusing core doing all the work would be a marble at the very center of that beach ball, no more than a tenth of its width. Nearly all of the sun's enormous bulk is inert material sitting outside that marble-sized furnace, heated and lit by it, but not directly part of the fusion itself. The sun converts roughly 600 million tons of hydrogen into helium every second, and has been doing so second after second for 4.6 billion years, and yet because the sun's core holds so much hydrogen to begin with, that furious rate of consumption has only used up about half of the usable hydrogen fuel available at the core so far. The sun, in other words, is a star in the prime of its life, calm on the outside, running hard on the inside, with a fuel gauge that is now unmistakably past its halfway point. This is where the story of the sun's transformation begins, not with drama, but with bookkeeping. Every second that passes, a little more hydrogen at the core becomes helium, and helium does not fuse nearly as easily as hydrogen does. Helium is heavier, and fusing it requires far higher temperatures and pressures than the sun's core can currently reach. So, as helium quietly accumulates at the sun's center, it does not fuel anything. It just sits there, inert, like ash slowly filling the bottom of a fire that is still burning above it. That accumulating ash is the first patient step toward everything that follows. A star that will eventually run out of easy fuel and have to change its shape, its size, and its behavior to cope with that. To understand why the sun cannot simply keep doing what it is doing forever, it helps to look more closely at what is actually happening inside that marble-sized core at the sun's center. The process is called the proton-proton chain, and despite the intimidating name, its basic idea is straightforward. 4 hydrogen nuclei, which are just single protons, are gradually combined into one helium nucleus made of 2 protons and 2 neutrons, releasing energy at several steps along the way. The first step is the hardest. 2 protons have to collide with enough force to briefly stick together, despite both carrying a positive electric charge that violently repels them. This almost never happens. In fact, a given proton at the Sun's core will bounce around, colliding with its neighbours, for an average of several billion years before it succeeds in fusing with another one. The Sun's core is on a per-particle basis, an almost absurdly slow furnace. What it lacks in speed per particle, it makes up for in sheer numbers. The Sun's core holds so many protons that even at a success rate measured in billions of years per particle, hundreds of millions of tons of hydrogen are converted every single second. Once that first difficult fusion happens, the resulting particle is unstable and quickly transforms, through a process governed by what physicists call the weak nuclear force, into a slightly different, stable particle called deuterium, along with the release of a positron and a nearly massless particle called a neutrino. That neutrino barely interacts with anything at all. It is created at the Sun's core and, remarkably, passes straight through the rest of the Sun and out into space in about 8 minutes, as if the Sun's enormous bulk were barely there at all. Trillions of these solar neutrinos pass harmlessly through every person on Earth every second, unnoticed, unfelt, gone. From there, the deuterium quickly fuses with another proton to form a light form of helium, and finally, 2 of those light helium nuclei collide and fuse into the stable, ordinary helium that will make up the growing ash pile at the Sun's core. Each full completion of this multi-step chain converts a tiny amount of mass directly into energy. Following the same principle Einstein described with his famous equation relating mass and energy. It is a genuinely small amount of mass lost per reaction, but the Sun runs an almost unimaginable number of these reactions every second, and that is more than enough to light a solar system. The energy released at the core does not travel outward as sunlight right away. Instead, it emerges first as an extremely high-energy form of light called a gamma ray, which then spends an extraordinarily long time working its way outward through the Sun's dense interior. It gets absorbed and re-emitted, scattered in a new random direction, absorbed again, over and over, in a slow drunken stagger, outward through hundreds of thousands of kilometers of solar material. Estimates for how long a single packet of that energy takes to random walk its way from the core to the visible surface range from tens of thousands of years to considerably longer. Only in the outer third of the Sun does that energy switch to a faster method of transport, physical churning of hot material rising and cool material sinking, called convection, which carries it the rest of the way to the surface in a matter of weeks. So the sunlight warming a person's face on any given afternoon did not just leave the Sun's core. It represents energy that was generated inside the Sun long before, in some cases tens of thousands of years earlier, and has only just now finished its slow, bumping, indirect journey out to the surface and across the roughly 150 million kilometers of empty space between the Sun and Earth, a final 8-minute hop that, unlike the light itself, is comparatively instantaneous. Every photon of sunlight is a message from the Sun's deep past, carrying proof that fusion has been running, faithfully, this entire time. This whole intricate, patient machine depends on one simple condition, that there is still enough hydrogen at the core, packed densely enough, at high enough temperature, for the chain to keep running at the rate needed to hold up the Sun's own weight. That condition will not last forever, and the changes that begin when it finally fails are exactly what turn a calm, dependable star into something far more dramatic. Every second, a little more of the Sun's core hydrogen becomes helium, and that helium does not go anywhere. It sinks toward the very center of the core because it is denser than the hydrogen around it, and it simply accumulates there, an inert ball of ash growing quietly at the heart of an active furnace. This is happening right now, and has been happening for the Sun's entire 4.6 billion year life so far. The consequences of that slow accumulation are not obvious on human timescales, but they are relentless. As the amount of usable hydrogen fuel at the core shrinks, and the inert helium ball at the very center grows, the core has to compensate to keep producing enough energy to support the Sun's weight. It does this the only way available to it. It contracts slightly and heats up further, which speeds up the remaining hydrogen fusion happening around the growing helium ball. A slowly shrinking, slowly heating core burning its remaining hydrogen a little faster is, in effect, the Sun quietly borrowing against its own future to keep the present stable. This has a real, measurable consequence that most people never hear about. The sun is not the same brightness it was billions of years ago, and it will not be the same brightness billions of years from now. Astronomers estimate that the sun has already grown roughly 30% brighter than it was when it first began fusing hydrogen 4.6 billion years ago, purely from this slow core contraction and compensating fusion rate increase, and it will continue to brighten, gradually, for as long as it remains on the main sequence, the technical term for this current stable hydrogen burning phase. This gradual brightening matters more than it might seem, because it means the sun's stability is not really a flat plateau. It is a very long, very gentle upward slope, with the star inching hotter and brighter century after century, so slowly that no human civilization has ever noticed it happening, yet so persistently that current models predict it will eventually make Earth too hot for liquid water on its surface, long before the more dramatic changes described later in this story even begin, possibly in about 1 billion years, well before the sun becomes a red giant. Eventually, though, gradual brightening will not be enough. There is a hard limit to how long hydrogen fusion at the core can keep pace with the sun's needs, because eventually there simply will not be enough hydrogen left at the core to fuse. Current models predict that in roughly 5 billion years, the core will have converted almost all of its available hydrogen into helium, leaving a dense ball of nearly pure helium at the sun's center, with no fuel of its own that it can yet use. At that point, the core fusion that has held up the entire structure of the sun for its whole life so far will start to falter, because there simply is not enough hydrogen left at the density and temperature needed to sustain it. And when the fusion that has been holding gravity at bay for 10 billion years finally starts to lose its grip, gravity does not wait politely. It begins to win, and the core starts to do something it has never done before across the entire main sequence life of the sun. It starts to collapse. That collapse sounds like exactly the kind of catastrophe a viewer might expect from an Earth running out of fuel. It is not, or at least, not directly. What that core collapse actually triggers is stranger, and in its own way, more dramatic than a simple failure, because a shrinking, heating helium core does not shut this down. It reignites a completely new kind of fusion in the layer of hydrogen still surrounding that helium ball, and it is this new fusion, paradoxically, that begins the process of turning the sun into a monster. When the sun's core finally runs out of hydrogen to fuse, roughly 5 billion years from now, the core does not simply switch off. Instead, gravity, freed from the balancing outward push of core fusion, pulls the now nearly pure helium core inward, compressing it. That compression, driven purely by gravity acting on a fuel-exhausted core, raises the temperature of a thin layer of hydrogen-rich material immediately surrounding the helium core, a shell just outside the dead center of the star. That shell of hydrogen, heated by the collapsing core beneath it, becomes hot and dense enough to ignite its own fusion, a process astronomers call hydrogen shell burning. This is a strange and important turning point. The star's main fusion engine has effectively moved. Instead of one compact fusing core at dead center, the sun now has an inert, contracting helium ball at its very center, wrapped in a comparatively thin, intensely fusing shell of hydrogen just outside it, wrapped in turn by everything else, the vast bulk of the sun that has always sat above the fusing region. This new arrangement produces far more energy and far more outward pressure than the old core fusion arrangement ever did, because the shell is now fusing hydrogen at a much faster rate to compensate for the shrinking heating core beneath it. All of that extra outward pressure has to go somewhere, and since it cannot push the collapsing core inward any faster, it pushes the sun's outer layers outward instead. The result is the single most important physical change in this entire story. The sun begins, for the first time in its life, to swell. It is worth pausing on how counterintuitive this is. A star with less fusible fuel at its center is what triggers it to grow larger, brighter, and eventually far more extreme than it has ever been. The dying core does not shrink the star, it grows it dramatically, because the shell burning surrounding that dying core produces so much extra energy that the star's outer envelope has nowhere to go but out and away. The timescale for this transition, once it truly begins, is fast by cosmic standards. Where the sun's stable main sequence hydrogen burning phase lasts roughly 10 billion years total, the swelling that follows the core's hydrogen exhaustion unfolds over a comparatively brief interval, commonly estimated at a few 100 million years for the sun to expand from its current size into a subgiant, and then a genuine red giant. A few 100 million years still sounds enormous on a human scale, but compared to the 10 billion year main sequence phase that came before it, it represents the star moving into a much faster, much more dramatic chapter of its life. As the Sun swells during this phase, its outer layers, spreading out over a much larger volume, cool. A gas that expands into a larger space and does not gain proportionally more energy tends to drop in temperature, and the Sun's outer surface is no exception. Even though the star as a whole is now producing more total energy than ever before, that energy is spread across a vastly larger surface area, and the surface itself cools from its current yellowish-white colour toward a cooler, redder colour, the same physical principle that makes a heated piece of metal glow orange rather than white as it cools. This combination, a much larger size paired with a redder, cooler surface colour, is exactly what astronomers mean by the term red giant, and it marks the beginning of the Sun's transformation from the small, steady, golden disk familiar throughout human history into something that will eventually dominate and then devour a significant part of its own solar system. The shell has ignited, the swelling has begun. What happens to the planets nearest the Sun, as that swelling continues, is the next and far more immediate part of this story. Once hydrogen shell burning takes hold around the Sun's shrinking helium core, the swelling that follows does not stop at a modest increase. Current models predict the Sun's radius will eventually grow to somewhere between roughly 100 and 200 times its present size, a scale of expansion that is difficult to hold in the mind using ordinary comparisons, so it helps to build it up in stages. Today, the Sun is about 1.4 million kilometers across, roughly 109 times the diameter of Earth. If the Sun were the size of a basketball, Earth would be smaller than a peppercorn sitting about 24 meters away. Now imagine that basketball swelling slowly, over hundreds of millions of years, until it is no longer basketball-sized, but large enough to fill an entire room, and then a house, and eventually large enough that its edge would reach out, past where that peppercorn-sized Earth used to orbit. That is the scale of transformation a red giant undergoes, translated down to something a person can stand inside. As the Sun's outer envelope expands to fill that much larger volume, its total surface area increases enormously, by a factor of thousands compared to today. This has a curious, almost paradoxical effect on the Sun's surface temperature, even as the star as a whole releases far more total energy than it does today. Thanks to the faster hydrogen shell burning happening beneath its swollen envelope, that energy is now spread across a surface area so much larger that the temperature at any single point on that surface actually drops. The Sun's visible surface, currently around 5,500 degrees Celsius, is expected to cool to somewhere around 3,000 to 300 to 500 degrees Celsius once it becomes a full red giant, a temperature drop of roughly 2,000 degrees even as its total light output climbs to somewhere between 1,000 and 3,000 times what the Sun produces today. That combination of vastly larger surface area combined with a lower surface temperature is precisely what gives a red giant its name and its colour. A cooler surface radiates more of its light in the red and orange part of the visible spectrum rather than the yellowish-white a hotter surface produces. The same basic physical principle that makes a cooling ember glow red rather than white. A red giant is not brighter because it burns hotter at any given point on its surface. It is far brighter overall and appears redder because it has become almost unimaginably larger, and total light output depends on both surface temperature and surface area together. As the outer envelope of the Sun expands this dramatically, it also becomes far less tightly bound by the Sun's gravity than the material sitting deep inside the star today. Gravity at the surface of an object depends on distance from that object's center, and as a red giant's outer layers puff outward to hundreds of times their former distance from the core, the Sun's gravitational grip on that outermost material weakens substantially. This weakly held outer envelope becomes increasingly easy to disturb, to push outward, and eventually, as later chapters will describe, to lose into space entirely, in slow but steady streams of gas leaking outward from the swollen giant. The swelling itself, importantly, happens gradually enough that it unfolds over hundreds of millions of years rather than days or years, which means there is no single dramatic day when the Sun suddenly becomes a red giant. Instead, there is a long, continuous process of growth. First a modest subgiant stage swelling, followed by an accelerating expansion as the helium core inside continues shrinking and heating, and finally the full dramatic red giant phase, during which the Sun's outer edge sweeps outward past one planetary orbit after another, engulfing whatever lies in its path. Which planet is engulfed first, and how soon, depends entirely on how close that planet orbits, and the planet standing directly in that expanding giant's path first is the one currently closest to the Sun of all, Mercury. Mercury orbits the Sun at an average distance of about 58 million kilometers, closer than any other planet, completing a full orbit in just 88 Earth days. It is a small, airless, heavily cratered world, roughly a third the diameter of Earth, its surface baked by direct sunlight during its long days and plunged into deep cold during its long nights. Since it has essentially no atmosphere to hold or redistribute heat, it has looked, in broad strokes, much the same for billions of years, a battered grey world quietly circling closer to the Sun than anything else in the solar system. As the Sun swells into a red giant over hundreds of millions of years, following the sequence described in the previous chapter, Mercury's fate is essentially sealed the moment the Sun's outer envelope begins expanding past roughly 100 times its current size. Current models predict the red giant Sun will grow large enough to reach and swallow Mercury's entire orbit. There is no meaningful scenario in which Mercury escapes this outcome. Long before the Sun's visible surface physically reaches Mercury's orbit, the intense heat and radiation pouring off the swelling giant will already have stripped away any remaining trace of the planet's minimal surface material, vaporizing loose material and slowly eroding the little world's outer layers even before direct contact occurs. When the Sun's outer envelope does physically reach and pass Mercury's orbit, the small planet will be engulfed entirely, plunged inside the tenuous, gaseous outer layers of the star itself. A planet moving through even the very outer, thin layers of a red giant experiences a drag force from that surrounding gas, similar in principle to the way air resistance slows an object moving through Earth's atmosphere, except here the surrounding material is the outer atmosphere of an entire star. That drag steadily saps energy from Mercury's orbit, causing the little planet to spiral inward rather than simply riding along near the giant's new, much larger surface. Once Mercury spirals inward through the red giant's outer layers, deeper toward the hotter, denser regions closer to what remains of the Sun's structure, it will not survive as a coherent object. The temperatures and pressures inside even the outer envelope of a red giant, at the depths Mercury would reach as its orbit decays, are far beyond anything a rocky planet's structure can withstand. Mercury will be vaporized, its rock and metal turned to gas and blended into the vast, slowly expanding material of the star that swallowed it, the same star that once lit its long, silent days from 58 million kilometers away. There is a strange kind of symmetry in this. Mercury formed, according to the best current models of solar system formation, from the same swirling disk of gas and dust that formed the Sun itself, roughly 4.6 billion years ago. In its final moments, roughly 5 to 7 billion years from now, it will return that borrowed material to the very star it came from, dissolving back into stellar gas rather than persisting as a separate object. What took shape as a distinct small world will end, quite literally, by becoming part of the Sun once again. This event, whenever it occurs on the specific timeline models eventually settle on, marks the moment the Sun's transformation stops being a distant, abstract process happening deep in its own interior and starts directly consuming the solar system it has always presided over. Mercury will be the first planet lost, purely because it orbits closest and therefore has the least room to spare as the Sun's outer edge expands outward to meet it. It will not be the last. The very next planet outward, Venus, sits only a little farther from the Sun, and current models give it very little reason to expect a different outcome. Venus orbits the Sun at an average distance of about 108 million kilometers, nearly twice as far out as Mercury, and it is a very different kind of world. A planet almost exactly Earth's size, wrapped in a thick, crushing atmosphere made mostly of carbon dioxide, with clouds of sulfuric acid and a surface hot enough to melt lead. Hotter than any other planet in the solar system, not because it is closest to the Sun, but because its dense atmosphere traps heat through a runaway greenhouse effect. Even at its current, comfortable by comparison distance, Venus is already the hottest planet, a reminder that distance from the Sun alone does not determine a planet's temperature. As the Sun's red giant expansion continues past Mercury's now vanished orbit, Venus is next in line, and the extra 50 million kilometers of distance it enjoys compared to Mercury buys it, at most, a modest reprieve rather than any real safety. Current models predicting the Sun's maximum red giant radius, somewhere around 100 to 200 times its current size, place that eventual outer edge well beyond Venus orbit in most scenarios, meaning Venus faces essentially the same fate as Mercury, delayed by however long it takes the Sun's expanding envelope to cross that additional gap. Before the Sun's visible surface ever reaches Venus directly, the planet will already be enduring conditions far beyond anything its current thick atmosphere is built to survive. The red giant Sun, even before full engulfment, will be pouring out somewhere between hundreds and thousands of times its current light output, and Venus, sitting well inside the zone where that intensified heat matters most, will have its already crushing atmosphere stripped away entirely, boiled off into space long before the star's physical surface arrives to finish the job. Any remaining surface rock will begin to melt and vaporize under that heat, the same fate Mercury's surface material suffered at a slightly earlier stage in the process. When the Sun's outer envelope finally does expand outward to physically encompass Venus' orbit, the planet will be engulfed just as Mercury was, plunged into the diffuse outer atmosphere of the swollen star and subjected to the same orbital drag that pulled Mercury inward and down. Venus, being a somewhat more massive planet than Mercury, will take a little longer to have its orbit fully decayed by that drag, but the eventual outcome current models describe is the same. A slow inward spiral through increasingly dense and hot stellar material, ending in the planet's rock and remaining substance being vaporized and folded into the Sun's own outer layers. It is worth marking in human terms just how significant this loss is. Venus is, by mass and size, nearly a twin of Earth, the closest thing to Earth's equal anywhere in the solar system. Its destruction is not a minor footnote in the way the loss of small, airless Mercury might be treated. It represents the Sun consuming a genuinely Earth-scale world, a sobering marker of how far the red giant's reach eventually extends, and a clear signal of just how close that reach comes to Earth's own orbit, only a further 42 million kilometers beyond where Venus circles today. That remaining gap between Venus' orbit and Earth's is the single most consequential distance in this entire story, because it is the distance that determines whether Earth itself is swallowed outright like Mercury and Venus, or whether it narrowly survives, scorched and lifeless, in an outer orbit just beyond the red giant's final reach. Current models cannot yet say for certain which outcome awaits Earth, and that uncertainty, and what does seem clear regardless of how it resolves, is exactly where this story turns next. Earth orbits the Sun at an average distance of about 150 million kilometers, the very distance that has allowed liquid water, and everything that depends on it, to persist on its surface for billions of years. As the red giant Sun's outer envelope sweeps outward past Mercury and then Venus, the obvious next question is whether that expansion simply continues on to consume Earth as well. The honest answer, based on current models, is that astronomers do not yet know for certain, and the reason for that uncertainty is genuinely interesting. As the Sun swells into a red giant, it also loses a significant amount of its own mass, blown outward into space as a slow, steady stellar wind, far stronger than the gentle solar wind streaming off the Sun today. Current models estimate the Sun could lose somewhere between a quarter and a third of its total mass over the course of its red giant and later evolutionary phases. Losing mass weakens the Sun's overall gravitational pull, and a weaker gravitational pull allows the planet still orbiting it to drift slightly farther outward, the same way a ball on the end of a slowly loosening string will swing in a wider circle. This effect, sometimes called orbital expansion, works in Earth's favour, nudging its orbit outward, even as the Sun's swelling surface reaches inward to meet it. Whether that outward nudge is enough to save Earth depends on a close race between two competing effects happening on similar timescales: how fast the Sun's surface expands outward, and how fast Earth's orbit drifts outward in response to the Sun's mass loss. Different models, using different assumptions about the exact rate of the Sun's future mass loss, have produced different answers to this question over the years. Some calculations suggest Earth's orbit will drift outward, just enough to remain permanently beyond the red giant Sun's maximum reach, surviving as a scorched but intact world in a wider orbit. Other calculations incorporating a subtler effect called tidal drag, in which the swollen Sun's gravity very slightly slows Earth's motion, the same way it once slowed Mercury and Venus, suggest that drag could pull Earth's orbit back inward just enough to bring it within reach after all, reversing whatever advantage the mass loss effect provided. What is not in serious doubt, regardless of how that narrow race resolves, is that Earth's biosphere will not survive to see the outcome decided either way. Long before the Sun becomes a true red giant, its slow, steady main sequence brightening, described earlier in this story, is expected to push Earth's average surface temperature well past the point liquid water can persist, likely within about 1 billion years from now, hundreds of millions of years before the red giant phase even begins in earnest. Earth's oceans are expected to boil away entirely under that intensifying sunlight, its atmosphere gradually stripped by the same runaway heating that once turned Venus into the hottest planet in the solar system, leaving Earth a dry, scorched, likely lifeless world long before any question of direct engulfment becomes relevant. So the honest, careful version of Earth's story is not a single dramatic day of destruction, but a long two-stage decline. First, a slow loss of oceans and atmosphere as the sun brightens gradually over roughly the next billion years, turning Earth into something more like present-day Venus. And only much later, roughly 5 to 7 billion years from now, the final and still genuinely uncertain question of whether that dried-out husk of a planet is finally engulfed outright by the red giant sun's expanding surface, or survives barren and airless, drifting in a slightly wider orbit just beyond the star's reach. Either way, the Earth familiar to any person alive today, with its oceans, its atmosphere, and everything living on it, has an expiration date measured not in the billions of years often quoted for the red giant phase itself, but closer to 1 billion years from now, a sobering thought precisely because, compared to the 4.6 billion years the Sun and Earth have already existed together, that remaining span is a genuinely short final chapter. By the time the Sun reaches the peak of its red giant phase, whatever becomes of Mercury, Venus and Earth along the way, the transformation from the calm, dependable star described at the start of this story is essentially complete. The small golden disk that once sat comfortably behind a thumb held at arm's length has become something else entirely. An enormous, dim red, slowly pulsing sphere, spanning what would once have been a significant fraction of the entire inner solar system, its outer layers thin, tenuous, and extending outward for tens of millions of kilometers beyond where its compact, fusing core used to sit alone. Viewed from a surviving outer world, such as Mars, which is expected to remain safely beyond the Sun's reach throughout this entire process, the red giant Sun would no longer look like a disk at all in the way the Sun looks today. It would fill a dramatically larger portion of the sky, glowing a deep orange red rather than the familiar yellowish white, its light noticeably dimmer per unit area than today's sunlight, because a red giant's surface, as described earlier, is genuinely cooler than the Sun's current surface, even while producing far more total light overall thanks to its enormously larger size. That total light output is the part of this transformation that matters most for the wider solar system. Current models predict the red giant Sun's total luminosity, its overall light and heat output, will climb to somewhere between roughly 1,000 and 3,000 times what the Sun produces today, an increase driven almost entirely by the star's dramatically larger surface area rather than by any increase in temperature at any single point on that surface. This dramatic brightening pushes the solar system's habitable zone, the narrow band of distances at which a planet could plausibly hold liquid water, far outward, potentially out past where Mars orbits today, and possibly even out towards some of the large moons of Jupiter and Saturn, several of which are thought to hold significant amounts of water ice beneath their surfaces right now. This matters because it means the red giant phase, while catastrophic for the inner solar system, is not simply a story of universal destruction. It reshapes where warmth and light fall across the solar system, briefly and temporarily warming distant, currently frozen worlds that have never known conditions gentle enough for liquid water, even as it consumes the worlds that have always enjoyed exactly those conditions. Icy moons currently locked in deep cold far from the Sun could, according to some speculative models, briefly experience temperatures allowing subsurface ice to melt at their surfaces during this phase of the Sun's life, a strange temporary flowering of habitability on worlds that have never had it before, even as Earth's own long-standing habitability is being permanently extinguished closer in. The red giant phase itself, once fully underway, does not last especially long by stellar timescales. Current models estimate the Sun will spend somewhere on the order of a few 100 million years in this bloated, cooler, vastly brighter red giant state, continuing to fuse hydrogen in the thin shell surrounding its still inert, still contracting helium core, before the next major turning point in its life arrives. That turning point, when it comes, is triggered not by anything happening at the surface, but by conditions finally becoming extreme enough, deep inside that quietly contracting helium core, for an entirely new kind of fusion to ignite there for the very first time. That moment when it arrives is sudden, violent, and unlike anything that has happened inside the Sun before, even though remarkably, it produces almost no visible change at all from the outside. It is called the Helium Flash, and it marks the point where the Sun's slow, steady evolution briefly becomes something closer to an explosion, contained entirely within a region of the star smaller than Earth itself. Throughout the red giant phase described in the previous chapter, the Sun's helium core has continued doing exactly what it has done since hydrogen fusion first stopped there. Contracting under its own gravity and slowly heating up, with nothing yet able to fuse inside it and push back against that contraction. Helium itself requires far higher temperatures than hydrogen does before it can fuse, because helium nuclei carry twice the positive electric charge of a single hydrogen nucleus, and pushing two positively charged particles close enough together to fuse becomes dramatically harder as that charge increases. Eventually, current models predict the Sun's contracting helium core reaches a temperature of roughly 100 million degrees Celsius, more than 6 times hotter than the hydrogen fusing core the Sun has relied on for its entire main sequence life so far. At that temperature, helium nuclei finally begin fusing into carbon through a multi-step process called the triple alpha process, in which 3 helium nuclei combine to form 1 carbon nucleus, releasing a burst of energy in the process. Under ordinary circumstances, a newly ignited fusion source would simply cause the surrounding material to expand and cool slightly, gently throttling the reaction rate back down, the same self-correcting balance that keeps ordinary hydrogen fusion stable throughout most of a star's life. But the Sun's helium core, by this point in its evolution, exists in an unusual physical state called electron degeneracy, in which the core's density has become so extreme that its behavior is governed less by ordinary gas pressure and heat, and more by quantum mechanical rules about how tightly electrons can be packed together. A core in this degenerate state does not expand and cool the way an ordinary gas would when heated. It stays roughly the same size no matter how much hotter it gets, at least for a while, which removes the natural safety valve that normally keeps fusion under control. The result is the helium flash. Newly ignited helium fusion generates more heat, which would normally cause expansion and cooling, but because the degenerate core resists expanding, the extra heat instead simply drives the fusion rate even higher, which generates still more heat in a rapid runaway feedback loop. For a matter of mere seconds, current models estimate the core briefly generates energy at a rate comparable to the light output of an entire galaxy, tens of billions of times the Sun's current total luminosity, an almost unimaginable spike of energy generation, concentrated entirely within a volume smaller than Earth. Despite that staggering internal energy spike, the helium flash produces essentially no visible change to the Sun as seen from the outside. The layers of the Sun surrounding the core are so thick and so effective at absorbing and redistributing that burst of energy that almost none of it escapes directly as a sudden flash of visible light. The flash's true violence is entirely an internal event, briefly transforming conditions deep inside the star while the Sun's outward appearance continues on, largely undisturbed, at least for the moment. What the helium flash does accomplish, over the following minutes and hours as the initial runaway settles down, is to heat the core enough that it finally loses its unusual degenerate state and begins behaving like an ordinary gas again, expanding and settling into a new stable configuration capable of sustaining steady helium fusion going forward, rather than the brief runaway burst that first ignited it. With that new stability established, the Sun enters a genuinely new phase of its life, a star now fusing helium into carbon at its core, on top of continuing to fuse hydrogen in the shell surrounding that core, a layered, more complex furnace than anything it has run before. Once the helium flash settles into stable, sustained helium fusion, the Sun enters a phase of its life astronomers refer to, for stars of its mass, as the horizontal branch phase, characterized by a steady ongoing conversion of helium into carbon, and in smaller amounts, further fusion of that carbon with additional helium nuclei into oxygen, occurring continuously at the Sun's core. This is a genuinely new kind of fusion for the Sun, involving heavier nuclei and requiring far higher temperatures than the hydrogen fusion that powered its entire main sequence life, but it settles, once established, into a comparatively calm and stable arrangement, not unlike the original hydrogen-burning stability the Sun enjoyed billions of years earlier, just running at a different fuel and a different temperature. One of the more surprising features of this phase is that the Sun, having spent the previous few 100 million years swollen into an enormous red giant, actually shrinks back down somewhat once stable helium fusion begins, with a genuine fusion source now active at the core again, providing steady outward pressure from deep inside the star, rather than only from a thin shell farther out. The extreme, loosely bound outer envelope of the red giant phase settles inward and becomes more compact. Current models estimate the Sun during this helium-burning phase will be significantly smaller, and correspondingly, somewhat dimmer than it was at the absolute peak of its earlier red giant expansion, even though it remains far larger and brighter than the Sun appears today. This phase, once established, is expected to last roughly 100 million years, considerably shorter than the roughly 10 billion year main sequence hydrogen-burning phase that came before it, but still a substantial span of time, longer than the entire history of complex animal life on Earth up to the present day. Throughout this period, the Sun continues fusing helium into carbon and oxygen at its core, while a thin shell of hydrogen fusion continues just outside that core as well, meaning the Sun, at this point, is running two separate active fusion processes simultaneously, layered one around the other like the layers of an onion, each converting a different fuel into a heavier product. Carbon and oxygen, the products of this helium-burning phase, are worth pausing on because they are not simply waste products discarded and forgotten. These are the same elements that make up a significant portion of Earth's crust: the carbon dioxide in its atmosphere, the calcium carbonate in shells and coral, and the carbon backbone of every living organism on the planet, including every human body. None of that carbon or oxygen was present in the hydrogen and helium that made up the universe immediately after the Big Bang. Both elements were forged, in exactly the kind of stellar fusion process described in this chapter, inside the cores of earlier generations of stars, some of which lived and died long before the Sun itself ever formed. The Sun's own core, right now in this future helium-burning phase, is doing the same fundamental thing that earlier stars did, to produce the carbon and oxygen already present in Earth, in the oceans, and in every living thing that has ever existed there. As this helium-burning phase eventually nears its end, roughly 100 million years after it begins, the same basic pattern that ended the earlier hydrogen-burning phase repeats itself, but faster and with a heavier fuel. The core's helium supply, like its hydrogen supply before it, is finite, and as it depletes, the balance between fusion pressure and gravity inside the core once again begins to shift in gravity's favour. The core begins contracting again, exactly as it did after hydrogen exhaustion, and that renewed contraction sets the stage for the Sun's second, and considerably more dramatic, expansion into an even larger kind of giant star. This second swelling, unlike the first, will be the Sun's final major transformation before the fusion story comes to an end altogether, and it involves a kind of instability that the Sun has not yet experienced. A star that begins to visibly pulse, brighten and dim in irregular cycles as it struggles to hold two separate unstable fusion shells in balance around an increasingly inert and increasingly crowded core. Once the Sun's core has converted essentially all of its available helium into carbon and oxygen, the same basic sequence that followed hydrogen exhaustion plays out again, but this time layered on top of a more complicated structure. With no more fuel to fuse at the very centre, the now carbon and oxygen core begins contracting under gravity once more, heating a helium-rich shell surrounding it enough to ignite fusion there, while a hydrogen-rich shell farther out, left over from the earlier hydrogen-burning phase, continues fusing as well. The Sun now runs two separate fusion shells, one burning helium and one burning hydrogen, layered around an inert carbon-oxygen core that has for now run out of fuel entirely. Astronomers call this stage the asymptotic giant branch, and it drives the Sun into an even more extreme expansion than the first red giant phase described earlier in this story. Current models estimate the Sun, during this second swelling, could grow larger than it did during its first red giant phase, potentially exceeding 200 times its current diameter, large enough that its outer edge, in the most extreme estimates, could extend out to roughly where Earth's orbit sits today, regardless of whatever happened to Earth itself during the earlier expansion. This second phase is, by essentially every measure, more extreme than the first, larger, brighter, and considerably less stable. That instability is the defining feature of this phase, and it comes from the awkward physical arrangement of two separate fusion shells sitting close together around a shared core. The helium-burning shell, in particular, does not burn steadily the way ordinary hydrogen fusion does. Instead, it tends to build up unburned helium for a period, then ignite it in a sudden, brief runaway burst, not unlike a smaller-scale echo of the earlier Helium Flash, before settling down and beginning the build-up again. Astronomers call each of these repeating bursts a thermal pulse, and the Sun, during this phase of its life, is expected to experience a series of them, spaced years to centuries apart, each one temporarily brightening the star and pushing more material outward into its already loosely bound outer envelope. Each thermal pulse also drives a phenomenon called dredge-up, in which convection currents, driven by the pulse's sudden burst of energy, physically carry material fused deep inside the star, including freshly made carbon, up through the star's interior and into its outer visible layers. This is one of the primary ways carbon, made through fusion deep inside stars like the Sun, ultimately ends up mixed into the material a dying star sheds into space, material that can eventually become part of new stars, new planets, and, given enough time and the right conditions, new living things. During this asymptotic giant branch phase, the Sun's already weakly bound outer envelope, described earlier as loosely held even during the first red giant phase, becomes weaker still, and begins leaking away into space at a substantially increased rate, driven by a combination of radiation pressure, pushing on dust that condenses in the star's cooler outer layers, and the general instability introduced by the repeated thermal pulses. This is not yet the dramatic final shedding event described in the next chapter, but rather a steady accelerating drizzle of mass loss, a preview of the far more complete departure of the Sun's outer layers that is coming. By the end of this asymptotic giant branch phase, which current models estimate will last only a few million years, comparatively brief even by the standards of this story's later chapters, the Sun will have lost a substantial fraction of its original mass to this steady outflow. Its inert carbon-oxygen core will be more exposed and more tightly compressed than ever before, and the stage will be fully set for the final, most visually dramatic event of the Sun's entire life, the complete shedding of its remaining outer layers, revealing at last the small, hot, dense object that has been quietly forming at its centre all along. Toward the end of the asymptotic giant branch phase, the Sun's outer envelope has become so loosely bound to the rest of the star, and so thoroughly disturbed by the repeated thermal pulses described in the previous chapter, that it finally reaches a tipping point. Rather than continuing to leak away slowly, the remaining outer layers of the Sun begin streaming outward into space in earnest, driven onward by the intense radiation pressure from the star's remaining energy output, pushing against the dust and gas of the departing envelope. Current models estimate this final shedding of the Sun's outer layers occurs over a relatively short span, on the order of about 10,000 years, remarkably brief compared to the billions of years that came before it. As this outward streaming material moves away from what remains of the Sun, it does not simply vanish into the emptiness of space. It expands outward as a genuine physically structured shell of gas and dust, glowing faintly at first, and then, once the exposed stellar remnant at the centre becomes hot enough, glowing far more brightly, lit from within by ultraviolet light pouring off that exposed core. Astronomers call the resulting glowing shell a planetary nebula, a name that confusingly has nothing to do with actual planets. Early astronomers, observing similar glowing shells around other dying stars through comparatively primitive telescopes, thought their round, planet-like appearance resembled the fuzzy disks of gas giant planets, and the name stuck even after the true nature of these objects became clear. A useful comparison for what is happening here is to imagine a person carefully peeling the transparent outer wrapping from a piece of hard candy. The sweet, dense material at the centre, the object that actually matters going forward, is left exposed and intact while the thin, expendable wrapping drifts away, catching and scattering light as it goes. The Sun's planetary nebula phase works in much the same way. The core, the actual dense stellar remnant that has been slowly forming inside the Sun, through the entire sequence of events described in this story, is finally revealed, uncovered by the departure of everything that used to surround it. Planetary nebulae observed around other dying stars throughout the galaxy today display an extraordinary range of shapes. Some appear as simple, roughly spherical shells, others form delicate rings, hourglass shapes, or elaborate structures with multiple lobes and jets, depending on factors like the dying star's rotation, magnetic field, and whether it has a nearby companion star influencing the shape of the outflowing gas. The Sun, as far as current models can predict, does not have a close companion star, which suggests its own planetary nebula will likely take on a relatively simple, roughly spherical or slightly lopsided shape, rather than the more elaborate structures seen around some other dying stars. This glowing shell of gas, illuminated by the exposed, extremely hot stellar remnant at its center, is visible and detectable across enormous distances, which is precisely why astronomers have been able to observe thousands of planetary nebulae throughout the galaxy, capturing this exact stage of stellar death, happening to countless other stars similar to the Sun, at various points along the same process described throughout this story. Every one of those observed planetary nebulae represents a preview of what will eventually happen to the Sun itself, a genuinely useful source of direct evidence for a future event no human will ever witness firsthand. The planetary nebula phase itself is temporary, cosmically speaking. The glowing shell of gas continues expanding outward, thinning as it spreads across an ever larger volume, and dims correspondingly, fading gradually over tens of thousands of years, until it becomes too diffuse and too faint to detect at all, dispersing back into the broader interstellar medium, the thin gas and dust that fills the space between stars throughout the galaxy. What remains behind at the center, after the glowing shell has fully dispersed, is the true final form of the Sun, small, extraordinarily dense, and finally free of the fusion that has defined every earlier stage of its life. Once the planetary nebula has fully dispersed, what remains at the center is called a white dwarf, and it is, by any ordinary measure, a strange kind of object. Current models estimate the Sun's white dwarf remnant will contain somewhere around half of the Sun's current mass, all of the carbon and oxygen fused during the earlier helium-burning phases, compressed into a sphere roughly the size of Earth, a planet-sized object carrying half a star's worth of matter. A single teaspoon of white dwarf material, if it could somehow be scooped out and weighed on Earth, would weigh several tons, a density far beyond anything encountered in ordinary experience. This extraordinary density is possible because a white dwarf is no longer supported by fusion at all. There is no hydrogen or helium left to fuse inside it in any meaningful quantity, and no fusion pressure pushing back against gravity's pull. Instead, the white dwarf is held up entirely by the same quantum mechanical effect briefly described earlier during the Helium Flash. Electron degeneracy pressure, a pressure that arises purely from quantum mechanical rules, stating that electrons packed this closely together cannot all occupy the same state, and so resist being compressed any further, regardless of temperature. This is fundamentally different from every earlier stage of the Sun's life, all of which depended on an active balance between fusion and gravity. The white dwarf phase depends on no fusion balance at all, only on this strange quantum resistance to further compression. Having no fusion source, a white dwarf does not generate any new energy of its own. All the light and heat it continues to radiate come entirely from residual heat, energy left over from the star's earlier active life, slowly leaking away into space over enormous stretches of time. A newly formed white dwarf is extremely hot, often hotter at its surface than the Sun is today, glowing a hot white or blue-white color. But with no fusion replenishing that heat, it can only ever cool down from that point onward, never reheating, never reigniting, simply radiating its stored heat away into the surrounding darkness, century after century, for as long as anyone could possibly measure. This slow cooling happens remarkably slowly, because a white dwarf, despite being extremely hot, has a comparatively small surface area, roughly the size of Earth rather than the size of the Sun, through which to radiate that heat away, and because the dense, degenerate material inside it conducts heat differently than an ordinary star's interior does. Current models estimate it takes billions of years for a white dwarf to cool from its initial extreme temperature down to a noticeably cooler, dimmer state, and many billions more to cool further than that. White dwarfs that formed from stars that died billions of years ago, some of the oldest known in the galaxy, are still measurably warm today, evidence of just how slowly this final cooling process unfolds. White dwarfs are not a rare or hypothetical category invented for this story. Astronomers have directly observed and studied many of them throughout the galaxy, including one orbiting the bright star Sirius, visible to the naked eye from Earth on clear nights, whose faint companion, known as Sirius B, is itself a white dwarf roughly similar in mass to what the Sun will eventually become, offering astronomers a real, nearby, directly observable example of almost exactly the kind of object this story has been building toward across every previous chapter. This white dwarf, this small, dense, slowly cooling ember of carbon and oxygen roughly the size of Earth, is the true and final physical form of the Sun, the end state toward which every earlier stage of its life, the stable hydrogen-burning main sequence, the first red giant swelling, the helium flash, the second swelling, and the shedding of its outer layers, has ultimately been leading all along. There is no further fusion phase to follow it, no further transformation into something larger or more dramatic. From this point forward, the Sun's story is simply one of extraordinarily slow, patient cooling, continuing for longer than the universe has yet existed. Once the Sun has become a white dwarf, the story of its active life is effectively over, but the story of its existence continues, stretching out over a timescale that dwarfs everything that came before it combined. The white dwarf, having no fusion source and only its residual heat to radiate away, will continue cooling, slowly and steadily, releasing that stored heat into the surrounding darkness of space for an extraordinarily long time. With nothing left inside it capable of reigniting or reversing that gradual cooling. Current models estimate this cooling process. By the time the white dwarf has faded to a temperature too low to emit any meaningful visible light, will take somewhere on the order of trillions of years, a span so much longer than the current age of the universe, roughly 13.8 billion years, that it is difficult to express the comparison meaningfully using ordinary numbers. If the entire current age of the universe were compressed into a single day, the full cooling time of the Sun's eventual white dwarf remnant would stretch out to something closer to a decade on that same compressed scale. The universe, in other words, is astonishingly young compared to how long this final ember of the Sun is expected to persist. Astronomers give a name to the theoretical end state of this cooling process. A black dwarf, a white dwarf that has cooled so completely that it no longer emits any meaningful light or heat at all, fading into an inert, dark, extremely dense object, invisible except by its residual gravity and by blocking light from anything behind it. It is important to be clear that no black dwarf has ever actually been observed anywhere in the universe, and none is expected to exist yet, because the universe, at roughly 8 billion years old, is simply nowhere near old enough for even the very first white dwarfs ever formed to have finished cooling that far. A black dwarf remains, for now, a theoretical destination implied by current physics rather than a directly observed reality, and it will remain that way for an inconceivably long time to come. Throughout this entire cooling process, spanning trillions of years, the white dwarf remnant of the Sun is expected to remain gravitationally stable, holding its Earth-sized shape and its roughly half-solar mass essentially unchanged, supported the entire time by the same electron degeneracy pressure described in the previous chapter, barring some external disruption, such as a close encounter with another star pulling it apart or merging with it, something current models consider extremely unlikely, given how sparsely stars are actually spaced throughout the galaxy. The white dwarf simply continues existing, growing steadily dimmer and cooler for the entire remainder of this unimaginably long cooling process. It is worth returning at the very end of this story to where it began, a small, steady, golden disk that has looked the same throughout the entirety of human history, currently about halfway through its stable hydrogen-burning main sequence life. Everything described across this entire episode, the gradual brightening, the exhaustion of core hydrogen, the swelling into a red giant, the loss of Mercury and Venus, and very likely Earth, the helium flash, the second swelling, the shedding of the outer layers into a planetary nebula, and the final collapse into a slowly cooling white dwarf, unfolds across a timeline stretching from roughly 5 billion years from now, for the beginning of the red giant phase, out to trillions of years from now, for the white dwarf's eventual near-total cooling. None of this is a prediction of doom arriving anytime soon, and none of it is unique to the Sun. Every star of roughly the Sun's mass throughout the galaxy, and there are a great many of them, is expected to follow essentially the same sequence, at its own pace, on its own timeline. Far more massive stars, dozens of times heavier than the Sun, meet a much more sudden and violent end, collapsing catastrophically and exploding as supernovae rather than gently shedding their outer layers, but the Sun is not massive enough for that particular fate. Its ending, when it eventually comes, will be quiet, patient and slow, a monster only in scale, never in temperament, fading gently into the dark exactly the way it has always, patiently, done everything else. Every star tells the same story in different words. Gravity pulls inward, fusion pushes back outward, and the story ends the moment the fuel runs out, and gravity finally gets the last word. For the Sun, that ending is not an explosion. It is a slow, patient collapse into something small, hot and quiet, a white dwarf no bigger than Earth, carrying the mass of a star and cooling for longer than anyone can meaningfully imagine. Mercury and Venus will already be gone by then, swallowed whole. Earth's fate sits closer to a coin toss than most people expect, but even in the kindest version, its oceans boil away long before the final act arrives. None of this happens soon. The Sun has perhaps 5 billion more years of steady, reliable hydrogen fusion ahead of it before any of this begins, which is longer than life has existed on Earth so far. But it is coming the way winter comes, the way every fire that is not fed eventually goes out. The sun that lights every day of every life that has ever been lived is in the end temporary. It will become a monster, and then it will become an ember, and then slowly it will fade into the dark like every star before it. What is left over from that fading, the carbon and oxygen locked in its core, is the same raw material that once became the water in Earth's oceans and the calcium in human bone. Stars end so that the next generation of stars and worlds and possibly minds can begin from what they leave behind.